So let's know how pulse oximeter works. The basic principle of pulse oximeter is based on the different light absorbance properties of oxyhemoglobin and deoxygenated hemoglobin. If we put up a graph of molar extinction ratio, and which is basically absorbance coefficient, and wavelength of light, then we'll see that oxygenated hemoglobin and deoxygenated hemoglobin have a different type of absorbance. Around 660 nanometer, the oxygenated hemoglobin, which is red, oxygenated hemoglobin absorbs very less light, and in like 940 nanometer, which is basically IR, the deoxygenated hemoglobin absorbs very less light, which is evident by the fact that arterial blood, which is highly oxygenated, is bright red in color, which means they do not absorb the red part of the wavelength. Now, how a pulse oximeter works. In pulse oximeter, there is always two parts. We have our finger, and there is a part upper and a part lower. Okay, so there is two light emitting diodes in one part, and in other part there are two receivers. The two light emitting diodes emit IR rays in the 940 nanometer wavelength, and another releases red light in 660 nanometer range, and the two photodetectors detect the light. Now we have Beer-Lambert's law. What is Beer-Lambert's law? Beer-Lambert's law states that absorbance is equal to a constant, which is the molar extinction ratio, which is a definite particular constant for a definite substance for a definite light wavelength, into the concentration of that substance into the distance between this emitter and receiver. Okay, so in this case we can measure the absorbance. We know the molar extinction ratio of oxygenated and deoxygenated hemoglobin at this wavelength and at this wavelength, and we know the distance between them, so the concentration we can get. But there is a problem in that, because in the finger there is arteries, there are veins, there are various kind of bones and tissue and everything. So, and veins have oxygenated hemoglobin also. So we have to exclude these other parts of the reading, because we only want to determine the oxygenated hemoglobin concentration in arterial blood. So how do we do that? We do that because this is pulse oximeter, not oximeter, pulse oximeter. We have to measure the pulse. So the distance when a pulse happens, there is expansion in the finger because of the blood volume, expansion in arterial blood. So you see there will be a graph like this displayed in pulse oximeter. Okay, so this part which is pulsatile in nature, this is only due to artery, and the part which does not change, be it systole, be it diastole, this is due to everything other than the arterial blood. So we can say this is the AC component of the reading and this is the DC component of the reading. Now what do we do with this value? We calculate a ratio. The ratio is of absorbance in red light, absorbance of red light in the AC component divided by absorbance of red light in the DC component divided by absorbance of infrared light in AC component by absorbance of infrared light in DC component. We call this R value. We call this R value. So what this R value does? Let's see if I have high oxygen saturation. In that case, we know from there the oxygenated hemoglobin will more absorb IR spectrum. So IRAC will be high and ARAC will be low. So the R will be low itself. And if we have low oxygen saturation, then deoxygenated hemoglobin will absorb red light more. Then red AC absorbance will be high and infrared AC absorbance will be low. So it will have a high value. So there we can create a graph like this of SpO2 and R value, that when SpO2 is 100 it is low and SpO2 is less, R value is high. We use this principle to actually measure the SpO2 in only 70% to 100% of SpO2, because the R value is a experimental data. We actually take volunteers and have them respiration in low oxygen conditions and confirm their oxygen saturation by arterial blood gas measurement, and then we have them put up a pulse oximeter and measure the R value, and then we denote a R value for that specific oxygen concentration. But for basic human ethics, we cannot do this experiment with human volunteers below 70% oxygen concentration. So we don't know what is the exact R value will be if there is, say, 30% oxygen concentration. So we only have data for 70% to 100% SpO2, and their R value. So in the 70% to 100% range, we can say that this is experimentally proved data. But when it goes below 70%, it is only extrapolated data. So we are not sure about the data below 70% of oxygen concentration. So we should not trust it either.